programmed as a sequential driven program, and it is difficult to implement them as a concurrent processing FSM. So concurrent processing is sequential, is it is one after the other, and when I say concurrent processing, so doing some part of the program and stopping that for a while and switching to the next program, doing that for some more time, the other program, and stopping that and again switching back to the previous program and continuing from the point where it was left out. This is something called as sequence driven program, concurrent processing, but that is not possible with the FSM, finite state machine model. You cannot do concurrent processing in the FSM. So, or it is very difficult to do concurrent processing with the finite state machine model. So this limitation can be overcome by using the another finite state machine modeling called as concurrent finite state machine model or hierarchical finite state machine model. Now, so HCFSM is an extension to FSM. That is why FSM used to support only the sequence driven program, but now HCFSM is extended even in order to support the concurrency and hierarchy. Now, how it supports concurrency and hierarchy? So by using something called as AND or decomposition of the states together. And HCFSM uses something called as state charts in order to capture the states, transition, and events and actions. Okay, so I have the example here, sequence program model. In sequence program model, the functions or the processing requirements are executed in sequence, one after the other. And it's something like conventional procedural programming. Even in procedural programming, what happens? Everything is done sequentially, one after the other. So FMs are good choice. This finite state machines are good choice for sequential program modeling. So another important tool used for modeling sequential program is flowchart. So this is well known because even when you have written the C programs, for every C program you used to write the flowcharts, because everything used to happen sequentially one after the other. Now FSM, finite state machine model approach, represents the states, events, transitions, and actions, whereas the flowchart model models the execution flow. So this FSM, if I take, it's going to represent all these things, the states, events, transitions, and the actions. So the flowchart models the execution flow, how the execution will flow. So now we consider this example now, seat belt warning example, how it is sequentially programmed. So this is the sequential program for the seat belt warning, and there is also the flow chart which shows how the control flows here. Now we have the macros on, initialized to 1, macro again off, initialized to 0, and macro, one more macro yes 1, and one more macro no is initialized to 0. We have the function with the name seat belt var. So within this function we have wait 10 seconds. Now wait for 10 seconds, because the moment the user turns on the ignitions, it waits for 10 seconds for the user to fasten the seat belt. So that is seat belt 1. So wait 10 seconds, and if check ignition on, so if the ignition on and the seat belt is off, that means the user has not turned on the seat belt, fastened the seat belt, set the timer for 5 seconds. So wait for 5 seconds, and then in this 5 seconds, if the user is not fastening the seat belt, start the alarm and check this. While seat belt is off, that means and the ignition is off and the timer is on, stop the alarm. So as long as this is that, you just start the alarm. So any one of this is done, so come out and stop the alarm. Next type of computational model that can be used for embedded system design is concurrent or communicating process model. So here in the sequential, everything was going sequential one after the other. Now that was the major disadvantage of the sequential programming model. Why? Because it leads to poor processor utilization. Now, why poor processor utilization? Because if, say, some process is executing sequentially, and that process wants to perform some IO waiting or sleep for the specified duration. So it's not possible for the processor to just go and execute the another ready program, because it is sequential. The processor waits until the process finishes its IO waiting or finishes its specified sleep duration. It will wait. That means the processor is sitting idle until the process finishes its IO operation or finishes its specified sleeping time. So now that leads to what poor processor utilization in the sequential programming model. Now and the processor utilization can be increased by using the concurrent processing model. Now what concurrent processing model will do is it will divide or split the task into multiple subtasks, and it is possible to tackle the CPU usage effectively. Now what, after doing splitting the task into multiple subtasks, so the CPU will start executing one subtask at a time, and if that subtask wants to undergo some wait or some sleep mode, or if it wants to undergo some input output operation, now the CPU will simply switch to the next subtask and it will start executing it. So with this you can keep the CPU busy, always, and you can have the better processor utilization. Now here, that is the advantage. One is CPU utilization or the processor utilization can be increased, but it has additional overhead, in task scheduling and task synchronization. Since the CPU is switching now from one subtask to the another subtask, so synchronizing between these subtasks is a challenging task. So now as an example for the concurrent processing model, again we are taking the seat belt warning system. Now how the seat belt warning system can be split into various tasks, various subtasks. So these are the various subtasks what we can have. First thing is a timer's task for waiting 10 seconds. One subtask you can have this timer task for waiting 10 seconds, that is wait time timer task. And then task for checking the ignition key status, that is ignition key status monitoring task. And then seat belt status monitoring task, alarm control task, alarm timer task. There are 5 tasks. This seat belt warning system, now it is divided into 5 subtasks like this, and we cannot execute them randomly or sequentially. Now what we do, we're going to execute them concurrently by synchronizing their execution. Now how to do that? So this is something like this. I have one more diagram. In my next slide I'll explain with respect to that. So now here I'll just point out these things. Create and initialize the events. So these are the events that we are identifying. So wait timer is one, wait timer expire is one event. So ignition on is one event, ignition off is another event, seat belt on is one more event, seat belt off is one more event, alarm timer start is one more event, alarm timer expire is one more event, and these are the tasks which are created. Create task, ignition status monitor, seat belt status monitor, alarm control, alarm timer. Now here is the concurrent processing. So now we don't have the things happening sequentially now, so they are happening concurrently. So this is the one task. These are all the tasks, 1 2 3 4 5 tasks I have, and appropriately they synchronize. Say for example, let me start from here. Seat belt status monitoring task while 1, if the seat belt is on, so set seat belt on. So now this event will trigger this. What it will do? So ignition off or seat belt on. Similarly, now I'll come to this. So set seat belt off. What this will do? This will trigger this. If ignition on and seat belt off, start the alarm. If the ignition is on and the seat belt, so the user has not fastened the seat belt, so what to do? So start the alarm. Next, set the alarm, set event alarm start. So this will trigger the alarm timer task. Wait for the event alarm start, sleep for 5 seconds like this, and set alarm timer expire. So come here, alarm timer expired, so this. So this is one event is triggering the execution of another. So that means nothing is happening sequentially here. It is all concurrent execution based on the event triggering. Next one is the next computational model that can be used for embedded system design is object-oriented model. And this object, they represent the real world entity. An object has two things. One, it has the data associated with it and the behavior associated with it. So the data which is associated with the object defines the state of the object, and the behavior, the object gets the behavior because of the methods or the functions what it supports. And so and this is the very good model for modeling any of the system. So why? Because it has a lot of advantages, because object-oriented model brings you the reusability, so maintainability and productivity. So that means you can, since it has very high reusability, productivity can also be increased. Now, object-oriented modeling, the object is an entity used for representing or modeling a particular piece of the system. Now, object represents the real world entity, and it has two things, the state and also the behavior. The object gets its state because of the members which are there inside the object, and the object has behavior because of the methods. And when an object makes a call to one of its method, so the object can change its state from one to the another. And a class is something like a blueprint of the object, or I can say an object is an instance of the class. So you can create any number of instances of a class. Okay, and then an object represents a state. A class represents the state of an object through the member variables, and object behavior through the member functions. That is what member functions, or you can also call them as methods. Now, and again, the member variables and the member functions. So the member data and the member methods can be what? So something like private, public, and protected. If it is private, so the member variables and the member functions can be accessed only within the class. If it is marked as public, so if the accessibility is marked as public, so the variables, member variables and the member functions can be accessed even outside the class as well. So, and there is something called as protected. If the member variables and the member functions are declared as protected or marked as protected, so the member variables and the member functions can be accessed only in the derived classes, something like that. So we stop here. Till now we understood what are the various computational models that can be used for designing and building the embedded systems. So we started from the very first data flow diagram. First computational model was the data flow diagram, which is mainly based on the data driven, and control flow diagram, which is mainly based on the control flow or the conditional execution, and the state machine model. And again, in that you understood the finite state machine model. So, and then finite state machine models are FSM, programmed by using the sequential programming technique, and that was the limitation. And just to overcome that limitation, one more came, that is HC FSM, that is hierarchical or concurrent finite state machine model. And next you understood the sequential programming model, concurrent programming model, along with the examples of the seat belt warning system and automatic tea or coffee vending machine. These are all the examples which we considered, and then the object-oriented modeling. So with this we have completed one more topic in the fourth module, that is computational models used in designing and building the embedded systems. And the next topic will be on the embedded firmware design and development. So we'll stop here. Thank you.